somewhere above the plane of an ordinary spiral galaxy, in a region where starlight thins and the darkness between suns stretches for trillions of kilometers, our journey begins. Not with engines, not with countdowns, but with a single quiet decision to leave the familiar behind and drift forward into the galaxy we call home, the Milky Way. From Earth, it appears as a faint band of light, a pale river drawn across the summer sky, visible only on the clearest, darkest nights, far from the glow of cities. Ancient civilizations gave it names. The Greeks saw spilled milk. The Romans called it a road. Cultures across every continent recognized it as something vast, something far larger than any mountain or ocean, something that stretched beyond the reach of imagination. And they were right. But none of them could have known what it truly was. The Milky Way is a barred spiral galaxy. It spans roughly 100,000 light years from edge to edge, perhaps a little more. Its disk is filled with between 100 billion and 400 billion stars, though the exact number remains uncertain even now. Around many of those stars, planets orbit. Around some of those planets, moons, and scattered between all of them, filling the spaces that appear empty to the eye, drifts an enormous quantity of gas, dust, molecules, and radiation that together form what astronomers call the interstellar medium. This is not empty space. It is the raw material from which stars are born and to which they eventually return. It is the fabric of the galaxy itself, and tonight we will be moving through it. Our journey will take us from the quiet outer reaches of the galactic disk, through the spiral arms where new stars ignite inside glowing clouds of hydrogen, past dense clusters of ancient stars that have orbited the galaxy since long before our sun existed, across the broad inner disk where stellar populations grow older and more tightly packed, and finally toward the galactic center where a supermassive black hole 4 million times the mass of our sun sits in patient silence, holding everything together. 90 minutes of travel, 100,000 light years of distance, and along the way, the story of how a galaxy lives. We begin here in the solar neighborhood. This is the region immediately surrounding our sun, a relatively calm stretch of the Orion Arm, sometimes called the Orion Spur, a minor structure branching between two of the Milky Way's larger spiral arms. The sun sits roughly 26,000 light years from the galactic center, placing it about halfway between the core and the outer edge of the disk. It is not a special location. There is nothing remarkable about our position within the galaxy. We orbit the center just as hundreds of billions of other stars do, completing one full revolution approximately every 230 million years. That orbital period is sometimes called a galactic year, and in the lifetime of our sun, now roughly 4.5 billion years old, it has completed only about 20 of these immense orbits. 20 slow circles around the center of the Milky Way, each one carrying our entire solar system through regions of space we will never consciously remember passing through. Right now, the stars nearest to us are unremarkable by galactic standards. Proxima Centauri, the closest, is a dim red dwarf a little over 4 light years away, too faint to see without a telescope. Alpha Centauri, its brighter companion system, is visible from the southern hemisphere as one of the brightest points in the sky. But even it is an ordinary pair of sun-like stars, doing nothing unusual. Barnard's star, Wolf 359, Lalande 211185. Sirius, these are our neighbors, scattered across a small bubble of space, perhaps 50 light years in diameter. Some are bright, most are dim. Nearly all of them are smaller and cooler than the sun. This is the nature of the galaxy. The stars we can see with our eyes on a dark night are not representative. They are the rare bright ones, the giants and supergiants, the unusual few whose luminosity carries across dozens or hundreds of light years. The overwhelming majority of stars in the Milky Way are small red dwarfs, faint and quiet, burning their hydrogen fuel so slowly that they will outlive our sun by trillions of years. But we are not staying in the neighborhood tonight. We are moving outward first, toward the edge of the galaxy, before turning inward for the long crossing toward the center. It is a deliberate choice. To understand the Milky Way, it helps to see where it ends, to feel the boundary where starlight fades and the emptiness of intergalactic space begins. So we rise gently above the plane of the disk. Below us, the stars spread out like a vast luminous sheet, thinner than you might expect. The Milky Way's disk, for all its width, is only about 2,000 light-years thick in most places. It is remarkably flat, like a vast plate of light, and from above, its spiral structure begins to reveal itself not as clean, geometric arms, but as ragged, branching streams of brightness wound loosely around a glowing bar-shaped core. The spiral arms are not solid structures. Stars do not remain locked inside them. Instead, the arms are density waves, regions where gas and dust compress slightly, triggering star formation, lighting up the lanes with the blue-white glow of young massive stars before those stars drift onward, and the wave moves through. It is the galaxy breathing, slowly, across hundreds of millions of years, and we are about to cross through several of those arms on our journey inward. But first, we continue outward, toward the edge. The stars grow thinner, the dust lanes fade, the temperature of the interstellar medium drops. Out here, the galaxy becomes quiet. Fewer stars form. The ones that exist are older, redder, slower. The spiral pattern dissolves into a sparse scattering of faint points. And beyond them, the halo, a vast, roughly spherical region surrounding the disk, home to the oldest objects in the Milky Way. We are leaving the familiar part of the galaxy now. And as the last bright stars fall behind us, the silence of deep galactic space settles around us like a blanket. This is where the journey truly begins. The outer disk of the Milky Way is a place most documentaries never visit. It is too quiet, too thin, too far from the bright nebulae and dense star fields that fill the popular images of our galaxy. But it is real, and it has a character of its own, and passing through it is part of understanding what the Milky Way truly is. Out here, perhaps 40,000 light-years from the galactic center, the concentration of stars drops noticeably. The spiral arms, so vivid closer to the midplane, lose definition. Gas clouds become sparse. Dust thins. The interstellar medium, which deeper inside the galaxy is rich with molecules and elements forged in ancient stellar furnaces, grows simpler and more diffuse. There is still hydrogen. There is always hydrogen. But it drifts in enormous lonely sheets, sometimes stretching across hundreds of light years without ever growing dense enough to collapse and form new stars. This is the galaxy's quiet margin, and yet it is not entirely lifeless. Scattered across the outer disk, faint red dwarfs continue their patient burning. Some of them have orbited the galaxy for 10 billion years or more, older than the Sun by a wide margin, formed in an era when the Milky Way itself was still assembling from smaller fragments of matter. These stars carry the chemical signatures of the early universe, low in metals, low in the heavier elements that later generations of stars would produce and scatter through their deaths. Astronomers call them metal-poor stars, and finding them out here in the galactic suburbs is one of the ways we reconstruct the history of the Milky Way itself. Every star carries a record of its birth, the elements it contains, the proportions of iron to hydrogen, carbon to oxygen, tell us when and where it formed, what the galaxy looked like at that moment, and what had already happened before it ignited. Reading those records is slow, careful work, but collectively, the stars of the outer disk form a kind of fossil archive, a library written in light and chemistry. Preserving the early chapters of the galaxy's life, we continue outward. The stars grow fewer, the darkness between them deepens, and then gradually, the disk ends. It does not end sharply. There is no wall, no boundary, no visible line where the Milky Way stops and intergalactic space begins. Instead, the stellar density simply fades. The last thin populations of stars trail off into a region astronomers call the galactic outskirts, a transitional zone where the disk dissolves into the halo. At roughly 50,000 light-years from the center, perhaps a little more, the recognizable structure of the spiral disk is gone. What remains is something older, something rounder, something far more ancient than anything we have passed so far, the galactic halo. If the disk is the Milky Way's visible body, the halo is its skeleton. It is a vast, roughly spherical region that envelops the entire galaxy, extending outward in every direction for hundreds of thousands of light years. It contains very few stars by comparison to the disk. It contains almost no gas, almost no dust, almost no raw material for new star formation. But what it does contain is extraordinary. Globular clusters. These are among the oldest surviving structures in the entire Milky Way. A single globular cluster is a dense, gravitationally bound swarm of stars, typically containing between 100,000 and 1 million individual suns packed into a sphere only a few dozen light years across. From a distance, they look like glowing jewels suspended in the darkness above the galactic plane. From within, they would be blinding a sky so crowded with nearby stars that night would never truly be dark. The Milky Way is home to roughly 150 known globular clusters. There may be more hidden behind the dust lanes of the inner galaxy. Most of them orbit the galactic center on long, elliptical paths that carry them high above and below the disk, looping through the halo in journeys that take hundreds of millions of years to complete. They do not follow the neat circular orbits of disk stars. They move on tilted, eccentric trajectories, remnants of an earlier, more chaotic period of galactic history. Many of these clusters are astonishingly old. Some have been dated to 12 billion years or more, placing their formation within the first 2 billion years after the Big Bang. They predate the current structure of the Milky Way. They predate the spiral arms, the thin disk, the sun, the Earth, everything familiar. When these clusters formed, the galaxy was still a loose, irregular collection of gas clouds and small proto-galactic fragments, colliding and merging in a slow gravitational dance that would eventually produce the barred spiral we see today. Omega Centauri is perhaps the most famous of them. Visible from the southern hemisphere as a faint, fuzzy patch of light, it contains roughly 10 million stars and spans nearly 150 light-years in diameter. Some astronomers believe it is not a true globular cluster at all, but the stripped core of a small galaxy that the Milky Way captured and absorbed billions of years ago. If that interpretation is correct, then Omega Centauri is a survivor, the dense heart of a galaxy that no longer exists, now trapped in orbit around the galaxy that consumed it. This is one of the quieter truths about the Milky Way. It has grown by consuming others. Over billions of years, smaller galaxies have drifted too close, been caught by gravity, and been pulled apart, their stars absorbed into the halo, and the disk, their identities erased. The evidence remains scattered through the halo like archaeological fragments, streams of stars, moving together on unusual orbits, chemical signatures that do not match the native population, clusters whose ages and compositions suggest foreign origins. The Milky Way is not just a galaxy. It is the accumulated remains of many galaxies, and this process has not ended, even now. Smaller satellite galaxies orbit the Milky Way, slowly losing stars to tidal forces, gradually being drawn inward. The Sagittarius dwarf elliptical galaxy, discovered in 1994, is one of the closest. It is being actively torn apart, its stars streaming out in long arcs that wrap around the Milky Way like ribbons. In a few 100 million years, it will be gone, fully absorbed, its stars indistinguishable from the rest of the halo population. We pause here for a moment, drifting in the halo, above the plane of the disk. Below us, the galaxy stretches out in a vast, thin sheet of light. From this vantage point, the spiral arms are visible as slightly brighter lanes, winding outward from a glowing central bar. The disk is luminous but impossibly flat, like a disk of light floating in an ocean of darkness. Around it, the faint points of globular clusters drift on their ancient orbits, and beyond everything, the emptiness of intergalactic space extends in every direction, broken only by the faint smudges of distant galaxies, millions of light years away. It is quiet here, the kind of quiet that exists only between galaxies, where the nearest star may be thousands of light years away, and the only light is the collective glow of the disk below. But we are not staying. We turn now. Our outward journey is complete. We have seen the edge, felt the thinning of the stars, passed through the ancient halo with its globular clusters and consumed galaxies. We have a sense now of the Milky Way's boundary, not a sharp line, but a gradual fade, a dissolving of structure into emptiness. And ahead of us, the long crossing inward begins. From the outer halo, back down through the disk, across the spiral arms, through star-forming regions and interstellar clouds, past older stellar populations and denser fields, all the way to the galactic center. The distance is immense, but the journey is gentle, and every light year we cross will bring something new. We descend slowly back toward the plane of the disk. The first stars begin to appear again, faint and scattered, the outermost members of the galactic population. Then more, then more. The familiar glow of the interstellar medium returns, a faint warmth in the spectrum, the presence of dust, the signature of molecules drifting between the stars. We are re-entering the Milky Way, and ahead of us, still tens of thousands of light years away, the first of the great spiral arms waits. The first sign of a spiral arm is not light, it is density. Long before the stars brighten and the nebulae appear, the interstellar medium begins to change. Gas that had been drifting thinly through the outer disk starts to gather. Hydrogen atoms, which had been separated by vast distances, find themselves drawn closer together by the gentle compression of the density wave moving through the galaxy. Dust grains, microscopic particles of silicate and carbon, forged in the atmospheres of dying stars, become more common. The space between stars, which had felt open and thin, begins to feel textured, layered, occupied. We are approaching the Perseus arm. This is one of the Milky Way's major spiral arms, a sweeping arc of enhanced star formation that wraps around the galaxy for tens of thousands of light years. It lies outside the Sun's position, farther from the galactic center, and it is one of the structures that gives the Milky Way its characteristic spiral appearance when viewed from above. The Perseus arm is not a wall, it is not a boundary. It is a region where the conditions for star formation become favorable, where gas compresses just enough, where temperatures drop just enough, where gravity begins to win its slow contest against pressure. And as we enter it, the galaxy comes alive. The first objects we encounter are molecular clouds. These are enormous concentrations of cold gas and dust, some of them spanning hundreds of light years, containing enough material to form thousands of stars. They are among the coldest places in the galaxy, with internal temperatures as low as 10 or 20 degrees above absolute zero. At these temperatures, hydrogen atoms bond together into molecules, and the resulting molecular hydrogen becomes the raw material from which new stars will eventually emerge. From outside, a molecular cloud appears dark. It absorbs the light of stars behind it, creating what early astronomers mistakenly called holes in the sky, regions where no stars seem to exist. In reality, the stars were there. They were simply hidden behind curtains of cold, dense dust. It was only with the development of infrared and radio astronomy in the 20th century that scientists could peer through these curtains and discover what was happening inside. Inside a molecular cloud, the process of star formation begins with collapse. A region of the cloud becomes slightly denser than its surroundings, perhaps disturbed by a passing shockwave from a nearby supernova, or compressed by the spiral arm density wave itself. Once that region crosses a critical threshold, its own gravity becomes strong enough to pull it inward. Gas falls toward the center, pressure builds, temperature rises, and over the course of tens of thousands of years, a protostar forms a hot, dense core of gas, not yet capable of nuclear fusion, but growing steadily as material continues to rain down from the surrounding cloud. This process is happening right now. In thousands of locations across the Perseus Arm, new stars are being born inside clouds we cannot see with ordinary light, their formation hidden behind the very material that feeds them. Some of these protostars will grow large and hot, destined to burn through their fuel quickly and die spectacularly, as supernovae within a few million years. Others will be small and dim, red dwarfs that will burn quietly for trillions of years, outliving not just their parent cloud, but perhaps the galaxy itself. The variation is extraordinary. From a single molecular cloud, stars of every possible size can emerge. The process is not perfectly understood. Why some regions produce massive stars, while others produce only small ones, remains one of the open questions in astrophysics. The initial conditions matter: the density of the gas, the temperature, the magnetic fields threading through the cloud, the turbulence created by nearby stellar winds and radiation. But the precise recipe that determines whether a collapsing core becomes a blue supergiant or a red dwarf is still being studied. What we do know is that star formation tends to happen in clusters. Stars rarely form alone. When a molecular cloud begins to collapse, it fragments into many cores, each one contracting independently, each one producing its own star, or sometimes a binary pair. The result is a young stellar cluster, a group of stars born from the same cloud at roughly the same time, sharing the same initial chemistry, but spanning a wide range of masses and luminosities. These clusters are the building blocks of the spiral arms. The most massive stars within them are extraordinarily luminous, producing intense ultraviolet radiation that ionizes the surrounding hydrogen gas and causes it to glow. This is how emission nebulae are created: vast regions of glowing gas, illuminated by the hottest young stars embedded within them. They are among the most visually striking objects in the galaxy, and they mark the locations where star formation is most active. We pass through one now. The gas around us glows faintly in shades that human eyes would perceive as red and pink, the characteristic color of ionized hydrogen. The light is soft, diffuse, spread across light years of space. Within it, young stars burn with fierce blue-white intensity, their radiation sculpting the gas into pillars, arcs, and cavities. Stellar winds, streams of charged particles, flowing outward from the surfaces of these massive stars, push against the surrounding cloud, compressing it in some places, dispersing it in others. This interaction between young stars and their birth clouds is one of the most important feedback mechanisms in the galaxy. The very stars that form from a molecular cloud eventually destroy it. Their radiation heats the gas, their winds push it outward, their supernovae, when they come, blast through what remains, scattering heavy elements into the interstellar medium and triggering new waves of compression that may seed the next generation of star formation elsewhere. It is a cycle: birth, illumination, destruction, dispersal, and eventually rebirth. The galaxy breathes through this cycle, and the spiral arms are where that breathing is most visible. As we continue deeper into the Perseus Arm, the stellar density increases: more stars, more clusters, more nebulae. The interstellar medium grows richer, threaded with filaments of gas and dust that stretch between star-forming regions like bridges. Magnetic fields, invisible but powerful, thread through the gas, influencing the way it moves and collapses. Cosmic rays, high-energy particles accelerated by supernovae and other violent events stream through the arm, at nearly the speed of light, adding another layer of energy to the environment. The Perseus arm is not a quiet place, even if it feels quiet to us at this pace. On timescales of millions of years, it is dynamic, turbulent, constantly evolving. Stars ignite and die, clouds form and dissolve. Shockwaves ripple outward from supernovae, colliding with other clouds, compressing gas, triggering new collapses. The arm is alive in a geological sense, changing too slowly for any individual observer to witness, but unmistakably active when viewed across the deep time of the galaxy's life. And yet, at our pace, drifting through at the speed of narration, it feels peaceful. The nebulae glow softly, the young stars burn steadily, the clouds drift, the dust catches faint light from distant sources, scatters it gently across the spectrum. There is no sound, of course. Bass carries no sound. But if it did, the Perseus arm would hum a low, sustained note made from the collective vibration of gas, gravity, radiation, and time. We are roughly 30,000 light-years from the galactic center now. The Perseus arm stretches ahead and behind us, curving gently as it wraps around the galaxy. From our position within it, the arm does not look like a distinct structure. We cannot see its edges. We cannot perceive its curvature. We are simply inside a region where stars are more common, where gas is denser, where the evidence of recent and ongoing star formation is everywhere. This is what it means to be inside a spiral arm. It is not a corridor. It is not a lane. It is a broad, gradual enhancement of density, a zone where the conditions favor creation, where the galaxy concentrates its generative energy, and once we pass through it, the density will thin again. The stars will spread out, and we will enter the quieter space between the arms, the interarm region, where the galaxy rests between breaths. But before we leave the Perseus arm, there is one more thing worth noticing. Among the young clusters and glowing nebulae, there are also older stars. Stars that were here before the current wave of formation. Stars that drifted into the arm on their galactic orbits and will drift out again in tens of millions of years. The spiral arm does not own its stars. It borrows them. The density wave moves through the galaxy at a different speed than the stars themselves orbit, and so stars enter and leave the arms continuously, like cars passing through a slow-moving region of traffic. This means the spiral arms are not permanent collections of the same stars. They are patterns sustained by the physics of the density wave, populated temporarily by whatever stars happen to be passing through at any given time. The pattern persists, the individual members change. It is one of the more elegant truths about spiral galaxies. Their most recognizable feature, the spiral arms themselves, are not objects. They are processes. They are the visible expression of a wave moving through a rotating disk of gas and stars, compressing material just enough to trigger the formation of bright new stars that light up the arm and make it visible from millions of light years away. We are passing through a process, not a place. And as we continue inward, leaving the Perseus arm behind, the glow of its nebulae fading slowly into the distance, we carry that understanding forward. The interarm space ahead is quieter, thinner, calmer, but it will not last. Another arm waits beyond it, and then another, each one a new expression of the same galactic breathing, the same density wave, the same ancient cycle of creation and return. The journey inward continues. The center is still far away, but every light year we cross brings us closer to the heart of the Milky Way, and the galaxy is only growing more interesting as we go. Between the spiral arms, the galaxy exhales. The dense star-forming regions of the Perseus arm have fallen behind us. The glowing nebulae, the young stellar clusters, the thick curtains of dust, all of it recedes into the distance, fading like a coastline, disappearing over a calm horizon. Ahead, the interarm region opens up. It is wider than you might expect. The gap between two major spiral arms can span several thousand light years, and crossing it feels like traveling across an open plain after leaving a forest. The stars here are not absent. They are simply less concentrated. The interarm region is populated by stars that have drifted out of the spiral arms on their galactic orbits, carried by their own momentum through the quieter space between the density waves. Most of them are older. The young massive stars, the ones whose blue-white light dominates the spiral arms, do not survive long enough to travel far from the regions where they were born. They burn through their hydrogen fuel in a few million years and explode as supernovae while still embedded in or near the arms. What remains in the interarm space are the longer-lived stars, the yellow dwarfs, the orange dwarfs, the vast population of red dwarfs, all of them quietly orbiting the galactic center, passing through arms and gaps alike on journeys that take hundreds of millions of years to complete. Our own sun is one of these. Right now, it sits within the Orion Arm, a relatively minor structure between the larger Perseus and Sagittarius arms, but it has not always been there. Over the 4.5 billion years since its formation, the sun has drifted through multiple spiral arms, spent long stretches in the interarm regions, and will continue this pattern for billions of years to come. The arms are not walls, they are waves, and the stars pass through them, the way boats pass through swells on a slow ocean. The interarm region we are crossing now has a different character from what we just left. The interstellar medium is thinner. Molecular clouds are rare. The conditions for star formation are largely absent. Not enough density, not enough compression, not enough gravitational instability to trigger collapse. The gas that exists here is warmer, more diffuse, spread across enormous volumes. It is the aftermath of the arm, material that was stirred and heated by the radiation and supernovae of the star-forming regions, now slowly dispersing into the broader galactic disk. There is a quietness to it that is difficult to convey. Not silence, the galaxy is never truly silent. Cosmic rays still stream through at nearly the speed of light. Magnetic fields still thread through the gas, invisible but measurable. Faint infrared radiation from distant dust grains still warms the background by fractions of a degree. But the visual density, the concentration of sources, the sense of proximity to other objects, all of it diminishes. Out here, the nearest star might be 5 or 10 light years away rather than 1 or 2. The nearest nebula might be hundreds of light years distant. The sky, if you could stand on a planet orbiting one of these interarm stars, would still be filled with the band of the Milky Way, but the individual details would be harder to pick out. The glow more uniform, the structure less obvious. This is the galaxy at rest between breaths, and it is worth pausing to appreciate what that means. The Milky Way is not static. It rotates, and its rotation is not uniform. The inner regions orbit the center faster than the outer regions. Stars closer to the galactic center complete their orbits in less time, while stars farther out take longer. This differential rotation is one of the fundamental properties of spiral galaxies, and it has profound consequences for the structure we see. If the spiral arms were made of fixed populations of stars, this differential rotation would wind them up within a few galactic rotations. The inner portions of each arm would move ahead of the outer portions, stretching the arm into a tighter and tighter spiral until it wrapped around the galaxy like thread around a spool. This is called the winding problem, and it troubled astronomers for decades before the density wave theory provided an elegant solution. The arms are not material structures, they are patterns. The density wave moves through the disk at its own speed, independent of the individual stars, compressing gas as it passes and triggering the formation of bright new stars that illuminate the arm. The stars themselves orbit at different speeds, depending on their distance from the center, entering and exiting the arms continuously. The pattern persists even as its constituent members change. It is one of the most beautiful examples in nature of a stable pattern, arising from the collective behavior of billions of individual objects. Here in the interarm region, we are between two of those waves. The compression of the Perseus arm is behind us. The compression of the next arm, the region where our Sun currently resides, and beyond it, the larger Sagittarius arm lies ahead. We are in the trough between two crests, a place where the galaxy's generative energy is at its lowest, where the material drifts freely, and where the stars that populate this space are simply passing through on their way to or from the next encounter with a spiral arm. It is tempting to think of these regions as empty. They are not. The interarm space contains roughly half of the galaxy's total stellar population at any given time. The stars are simply spread more thinly, their light less concentrated, their presence less dramatic. If you counted every star in the Milky Way and plotted its position, the spiral arms would appear as modest enhancements above a background that is already rich with stars everywhere. The arms increase the local density by perhaps 20 or 30%, enough to trigger star formation and create the visible spiral pattern, but not enough to leave the interarm space truly barren. We continue inward. The distance from the galactic center is now roughly 28,000 light-years and decreasing. Ahead, the first signs of another concentration of matter begin to appear. The gas grows marginally denser. A few more dust lanes become visible, dark threads running through the background star field. A faint molecular cloud drifts into view, small by galactic standards, perhaps a few dozen light-years across, too diffuse and too isolated to collapse into stars on its own. It is a remnant, possibly a fragment of a larger cloud that was disrupted during its last passage through a spiral arm, now slowly dispersing into the interstellar medium. These fragments are common between the arms. They are the debris of the star formation process, carried outward by stellar winds, scattered by supernovae, slowly dissolving back into the general background. Some of them contain interesting molecules, complex organic compounds, chains of carbon and hydrogen, traces of alcohol and formaldehyde, and other substances that would seem more at home in a chemistry laboratory than in the vacuum between the stars. Astrochemistry, the study of molecules in space, has revealed that the interstellar medium is far more chemically complex than anyone suspected a century ago. Hundreds of different molecules have been identified in interstellar clouds, some of them surprisingly large and intricate. This chemistry matters because it connects to a larger story, the story of how the raw material of life is assembled and distributed across the galaxy. The carbon, oxygen, nitrogen, and hydrogen that make up living organisms on Earth were all forged inside stars, expelled into space when those stars died, mixed into the interstellar medium, incorporated into new clouds, and eventually gathered into new planetary systems. The interarm space, with its drifting fragments and slowly mixing chemistry, is part of that cycle. It is the long, patient phase between the dramatic events of stellar birth and death, the quiet period when elements disperse, mix, and wait for the next round of compression to begin. We are now approaching the inner edge of the interarm gap. The stellar density is beginning to increase again. More stars, more dust. The faint glow of distant emission nebulae begins to appear ahead, barely visible, hinting at the presence of young hot stars somewhere beyond the intervening gas. The galaxy is becoming more populated, more active, more alive. We are entering the region that contains our own sun. The Orion arm, sometimes called the Orion spur, or the local arm, is the minor spiral structure that runs between the Perseus arm and the larger Sagittarius arm. For a long time, astronomers considered it a relatively insignificant feature, a short branch, connecting or bridging two of the galaxy's major arms, rather than a true arm in its own right. More recent observations have suggested it may be longer and more substantial than previously thought, extending for perhaps 20,000 light-years and containing a significant number of star-forming regions, but the debate over its exact nature continues. What is not debated is that it is home. Our Sun sits within the Orion Arm, roughly halfway between the galactic center and the outer edge of the disk. The familiar constellations visible from Earth Orion, Scorpius, Sagittarius, Cygnus are largely made up of stars within this arm, or visible through it. The great nebulae that populate astronomy textbooks, the Orion Nebula, the Eagle Nebula, the Lagoon Nebula, are star-forming regions within or near this structure. When we look up at the Milky Way from a dark site on Earth, we are looking along the plane of the galactic disk, and much of the bright detail we can see belongs to the Orion Arm and the neighboring regions of the Sagittarius Arm beyond it. Passing through the Orion Arm feels different from the Perseus Arm, though the underlying physics is the same. The star-forming regions here are closer to the Sun's position, which means they have been studied in far greater detail. The Orion Nebula, roughly 1,300 light-years away, is one of the most observed objects in the sky. It is a vast stellar nursery, a region where hundreds of young stars are emerging from a cloud of gas and dust, their radiations sculpting the surrounding material into intricate shapes. Deep within the nebula, the trapezium cluster, a tight group of 4 brilliant young stars, pours ultraviolet light into the gas, ionizing it, causing it to glow. These are the kinds of objects that make the spiral arms visible. Without their light, the arms would be nearly invisible, just subtle concentrations of gas and older stars, undetectable to the naked eye. It is the young stars, born in the density wave, that trace the spiral pattern and give spiral galaxies their distinctive appearance. They are the galaxy's way of showing its structure, its internal rhythm made visible through light. We do not linger here. Our Sun is somewhere in this region, orbiting quietly, accompanied by its 8 planets, its dwarf planets, its moons, its asteroids, its comets, all of it forming a tiny system, lost among billions of others. We do not stop to visit. The purpose of this journey is not to return home, but to cross the galaxy, and home is simply one more point along the way. Ahead, the Orion Arm begins to fade, and the glow of something larger emerges beyond it. The Sagittarius Arm, one of the Milky Way's major spiral arms, stretches across our path like a bright river of stars and gas. It is wider, denser, and more active than the Orion Arm. Its star-forming regions are more numerous, its molecular clouds are more massive, and through the gaps in the foreground dust, we can already see the warm orange glow of the denser regions of the inner galaxy beginning to assert itself behind it. The galaxy is getting brighter, the stars are getting closer together, the interstellar medium is growing richer, and for the first time, we can begin to feel the gravitational presence of the galactic center pulling everything inward, gently, patiently, across distances that reduce with every passing moment. We are now roughly 25,000 light-years from the center. The outer galaxy sparse, ancient, quiet is behind us. The inner galaxy dense, luminous, complex lies ahead, and the Sagittarius Arm is the threshold between them. We cross it next. The Sagittarius Arm announces itself differently from the Perseus Arm. When we crossed the Perseus Arm earlier in our journey, we were farther from the galactic center, in a region where the spiral structure was broad, relatively open, and populated by a mix of young and old stellar populations spread across wide stretches of space. The Sagittarius Arm is closer to the center. The galactic disk here is denser. The concentration of gas is higher. The molecular clouds are more massive, and the star formation rate, the measure of how many new stars ignite per unit of time, per unit of area, is noticeably greater. We are now roughly 22,000 light-years from the galactic center, and the difference is palpable. The background glow of the Milky Way, that diffuse luminosity created by the combined light of billions of unresolved stars, has brightened. The interstellar medium is thicker. Dust lanes are more frequent, darker, more defined. They cut across the field of stars like rivers of shadow, absorbing light from everything behind them and re-emitting it as faint infrared radiation, invisible to human eyes but measurable with the right instruments. The Sagittarius Arm is one of the Milky Way's major spiral arms. It curves inward from our position, wrapping around the galaxy in a sweeping arc that connects the outer disk to the complex structures of the inner galaxy. Along its length, some of the most luminous star-forming regions in the Milky Way reside vast complexes of molecular gas, young stellar clusters, and emission nebulae that pour light into the surrounding space with extraordinary intensity. From Earth, many of these regions are visible through binoculars or small telescopes. The Lagoon Nebula, roughly 5,000 light-years from the Sun, sits within the Sagittarius Arm. It is a massive cloud of ionized hydrogen, illuminated by the fierce radiation of young hot stars at its core, and it appears to the naked eye as a faint smudge of light within the constellation Sagittarius. Near it, the Trifid Nebula displays a striking pattern of dark dust lanes that divide its glowing gas into distinct lobes, a visual effect created by dense filaments of cold material, silhouetted against the emission behind them. These nebulae are not decorations. They are active stellar nurseries, places where the next generation of stars is being assembled from the raw material of the galaxy. Each one contains enough gas to produce thousands of stars, and each one is shaped by the complex interaction between gravity pulling inward and radiation pushing outward. The balance between these forces determines the size, shape, and the lifespan of the nebula, and it is never quite the same twice. As we pass through the Sagittarius Arm, the variety of stellar environments becomes apparent. Young blue stars, only a few million years old, burn in tight clusters near the densest parts of the molecular clouds. Around them, the gas glows. Farther from the clouds, older stars from previous generations of formation drift on their own orbits, their light yellower, their surfaces cooler, their lives far longer. Red giants, stars that have exhausted the hydrogen in their cores and expanded to enormous sizes, appear scattered among the population, their swollen atmospheres glowing with a warm orange light that contrasts with the blue-white brilliance of the younger stars nearby. And between the stars, there are remnants of those that have already died. Supernova remnants are common in active spiral arms. When a massive star reaches the end of its life, it collapses and explodes, ejecting its outer layers at speeds of thousands of kilometers per second. The expanding shell of debris plows into the surrounding interstellar medium, compressing it, heating it, creating a bubble of hot gas that can persist for tens of thousands of years. These remnants are visible at many wavelengths in radio, in X-rays, in infrared, and they play a critical role in the evolution of the interstellar medium. They mix heavy elements into the gas. They compress neighboring clouds, potentially triggering new episodes of star formation. They inject energy into the galactic disk, stirring the gas, preventing it from settling into a perfectly smooth, featureless layer. The galaxy is not a static object. It is a dynamic system, and the spiral arms are where that dynamism is most concentrated. Birth and death happen here in an ongoing cycle, each generation of stars altering the environment for the next, each supernova reshaping the cloud from which future stars will form. The elements that make up rocky planets, organic molecules, and living organisms are forged in stellar interiors and distributed through these explosions. The iron in blood, the calcium in bone, the oxygen in water, all of it passed through at least one star before becoming part of a planet. And much of that stellar processing happened in regions like this one, inside the spiral arms, where star formation is most vigorous. We are deep inside the Sagittarius Arm now, surrounded by a richness of stellar activity that would have been impossible in the outer galaxy. The sky, from any vantage point within this arm would be spectacular, filled with nebulae, clusters, and bright individual stars in every direction. The band of the Milky Way, as seen from a hypothetical planet orbiting one of these stars, would be brilliant, far brighter, and more detailed than what we see from Earth, because the line of sight toward the galactic center passes through denser and denser populations of stars, and it is toward the galactic center that we are still heading. As we move through the inner portion of the Sagittarius arm and begin to emerge from its trailing edge, the galaxy ahead of us changes character once more. The spiral structure becomes harder to trace. The arms, so distinct in the outer and middle galaxy, begin to blend together. The spacing between them narrows. The interarm gaps, which earlier in our journey provided clear stretches of relative emptiness, grow shorter and less well defined. Gas and dust are everywhere, thick enough in places to block visible light entirely, creating dark zones where optical telescopes can see nothing at all. This is the transition into the inner galaxy, the region within roughly 15,000 light-years of the galactic center, where the Milky Way's structure becomes more complex, more crowded, and more difficult to map from our vantage point within the disk. Much of what we know about this region comes from radio and infrared observations, wavelengths that can penetrate the heavy dust, obscuring the inner galaxy from optical view. Without those tools, the galactic center itself would be entirely invisible to us, hidden behind curtain after curtain of interstellar dust. Between the Sagittarius arm and the next major structure inward lies a region that astronomers have debated for decades. The Scutum Centaurus arm, one of the Milky Way's two primary arms, sweeps through the inner galaxy in a long, dense arc. Whether it connects directly to the galactic bar or originates from it, whether it is truly a single continuous arm or a collection of overlapping segments, remains a matter of ongoing study. Mapping the far side of the galaxy from within is extraordinarily difficult. The distances are vast, the dust is heavy, and the crowding of stars along the line of sight makes it challenging to determine which objects are nearby and which are far away. What is clear is that the stellar density continues to increase as we move inward. The number of stars per cubic light year grows. The interstellar medium becomes richer, more turbulent, threaded with stronger magnetic fields, and populated by more energetic particles. The gravitational environment changes as well. In the outer galaxy, stars orbit the center in nearly circular paths, moving at roughly similar speeds, the gravitational pull distributed across a broad, smooth potential. In the inner galaxy, the orbits become more complex. The gravitational influence of the central bar, a dense, elongated structure of stars spanning several thousand light years at the core of the Milky Way, begins to assert itself, perturbing the orbits of nearby stars and shaping the flow of gas in the surrounding region. The bar is something we cannot yet see directly from our current position. It lies ahead, deeper inside, closer to the center, but its influence reaches outward, sculpting the inner spiral arms, directing the flow of gas along its leading edges, creating resonances that affect stellar orbits thousands of light years away. It is the structural backbone of the inner Milky Way, and as we continue inward, its presence will become increasingly important to the story. For now, we are passing through the last clearly defined spiral arm on our inward journey. Ahead, the galaxy becomes denser, warmer, more complex. The neat separation of arm and interarm begins to dissolve. The inner disk is a different environment, older, more crowded, more influenced by the bar and the bulge and the growing gravitational dominance of the galactic center. We have been traveling inward for some time now. Behind us, the outer disk, the halo with its ancient globular clusters, the Perseus arm with its quiet star-forming regions, the interarm spaces, the Orion arm where our sun lives its unremarkable life, and now the Sagittarius arm with its massive nebulae and vigorous stellar nurseries. All of it lies in the distance, spread across tens of thousands of light years. Ahead, the galaxy grows brighter, the dust grows thicker, and the structures we are about to encounter have no equivalent in the outer galaxy. The inner Milky Way is a world unto itself, dense, luminous, complex, and ancient. Stars here have been orbiting the center for billions of years, many of them older than the Sun, their compositions reflecting an earlier, more metal-rich phase of galactic chemical evolution. The stellar populations shift. The thin disk which dominates the outer galaxy thickens. The thick disk, a broader, older component with a larger vertical scale height, becomes more prominent. Stars drift above and below the midplane more freely, their orbits carrying them through a wider range of heights than the tightly confined populations of the outer disk. And somewhere ahead, hidden behind the dust but unmistakable, in the radio and infrared spectrum, the galactic center waits. We are not there yet. We have thousands of light years still to cross, and the journey through the inner galaxy will bring its own discoveries. But for the first time, we can feel it not as a point, not as a destination, but as a presence, a gravitational anchor around which everything we have seen tonight is organized. The stars, the gas, the arms, the clusters, the halo, all of it orbits that center. All of it is held in place by the mass concentrated there. All of it is part of a single, enormous, slowly rotating structure that has existed for more than 13 billion years. The Milky Way is old, and the closer we get to its center, the more we will feel the weight of that age. The journey continues inward. The stars grow closer together. The dust grows thicker, and the light of the inner galaxy begins to fill the space around us, not as individual points, but as a continuous warm glow, the accumulated brightness of billions of stars too distant and too numerous to resolve individually. We are entering the deep interior of our galaxy, and everything is about to change. The inner galaxy is a different country. Everything we have crossed so far, the outer disk, the halo, the spiral arms, the interarm spaces, all of it existed at distances greater than 20,000 light years from the galactic center. Out there, the galaxy was relatively orderly. The disk was thin. The spiral arms were distinguishable. The stellar populations were spread across wide volumes, and the spaces between stars were generous enough to feel open, navigable, almost peaceful. Here, inside 15,000 light years from the center, the character of the Milky Way shifts in ways that would be immediately noticeable if we could see with our own eyes. The stellar density has increased substantially. Stars that were separated by several light years in the outer galaxy are now separated by smaller fractions. The interstellar medium, which in the outer regions drifted thinly between the arms, is now denser, warmer, more turbulent, compressed by the gravitational influence of the growing mass concentration toward the center. Magnetic fields are stronger, cosmic ray fluxes are higher. The entire environment is more energetic, more crowded, more complex, and the structure has changed. The neat spiral pattern that organized the outer and middle galaxy becomes increasingly difficult to identify here. The arms blend together, the interarm gaps narrow and eventually disappear. In their place, a more chaotic arrangement of gas clouds, stellar streams, and overlapping populations fills the inner disk with a richness that defies simple description. Mapping this region from our position within the galactic plane has been one of the most persistent challenges in modern astronomy, because the heavy dust that permeates the inner galaxy blocks visible light so thoroughly that optical telescopes can see almost nothing of the galactic center or the structures surrounding it. What we know about the inner Milky Way comes primarily from observations at other wavelengths. Infrared light, with its longer wavelength, passes through dust far more easily than visible light, allowing infrared telescopes to peer deep into the crowded central regions. Radio waves penetrate even more effectively, revealing the distribution of hydrogen gas, the locations of molecular clouds, and the presence of energetic phenomena that would be entirely invisible otherwise. X-ray and gamma-ray observations detect the highest energy processes regions, where matter is being heated to extreme temperatures, where particles are being accelerated to enormous speeds, where the most violent events in the galaxy leave their signatures in the electromagnetic spectrum. Together, these observations have revealed a galactic interior that is far more complex and active than the outer disk. One of the most significant structures in the inner Milky Way is the galactic bar. This is a dense, elongated concentration of stars that spans roughly 10,000 to 15,000 light years in length, oriented at an angle to our line of sight from the Sun. The bar is not a separate object from the disk. It is part of the disk, a region where the stellar orbits have been organized by gravitational resonances into elongated, non-circular paths that collectively create a bar-shaped overdensity at the center of the galaxy. Barred spiral galaxies are common in the universe. Roughly 2/3 of all spiral galaxies possess some form of central bar, and the Milky Way is now firmly classified among them. The presence of the bar was debated for decades, because observing it from within the galaxy is extraordinarily difficult. We are embedded in the disk, looking edgewise through billions of intervening stars and thick curtains of dust. Confirming the bar required careful infrared surveys, stellar velocity measurements, and comparisons with computer simulations of galactic dynamics. By the early 21st century, the evidence was strong enough to establish the bar's existence with high confidence. The bar influences everything around it. Its gravitational field is not symmetric. It rotates as a rigid structure, turning around the galactic center at a pattern speed different from the orbital speed of individual stars. This mismatch creates resonances specific distances from the center, where the gravitational influence of the bar interacts with the orbital motion of stars and gas in complex ways. At these resonance points, the orbits of stars can be deflected, gas can be funneled inward along the leading edges of the bar, and the spiral arms themselves may be generated or maintained by the bar's gravitational influence. Some models suggest that the Milky Way's spiral arms originate at the ends of the bar, emerging from its tips and winding outward through the disk. Other models propose that the arms are independent density waves that interact with the bar, but are not directly generated by it. The precise relationship between the bar and the arms remains an active area of research, complicated by the difficulty of observing the far side of the galaxy and the challenge of distinguishing between competing theoretical models using the available data. What is clear is that the bar channels gas. Along its leading edges, streams of molecular gas flow inward, funneled by the bar's gravitational potential toward the central regions of the galaxy. This gas flow feeds the inner structures of the Milky Way, supplying material for star formation in the central molecular zone and ultimately contributing to the mass concentration near the galactic center itself. The bar acts as a pipeline, connecting the disk to the core, transferring material from the outer regions of the inner galaxy toward the center across timescales of hundreds of millions of years. As we move closer, passing through the bar's domain, the stellar populations around us continue to change. The thin disk, which dominated the outer galaxy with its young stars, open clusters, and active star-forming regions, has been gradually joined by the thick disk, a broader, older component of the Milky Way that extends to greater heights above and below the galactic midplane. Stars in the thick disk are generally older than those in the thin disk, with different chemical compositions, reflecting the conditions under which they formed billions of years ago. Their orbits are more inclined, carrying them higher above and below the plane, giving the thick disk its characteristic puffiness, compared to the razor-thin younger population. In the outer galaxy, the thick disk is a subtle presence, contributing only a small fraction of the local stellar density. Here, in the inner galaxy, it becomes much more prominent. The two populations overlap and intermingle, creating a blended stellar environment where old and young stars, metal-rich and metal-poor, thin disk and thick disk, coexist in the same volume of space, disentangling these populations, determining which stars belong to. Which component requires detailed measurements of their positions, velocities, and chemical compositions, a task that modern surveys are beginning to accomplish with remarkable precision. Beyond the thick disk, another structural component begins to assert itself as we approach the center, the bulge. The galactic bulge is a large, roughly box-shaped or peanut-shaped concentration of stars surrounding the galactic center. It extends several thousand light years above and below the plane, and several thousand light years outward from the center, forming a three-dimensional structure that is visually distinct from the flattened disk. When we look at other spiral galaxies from the outside, the bulge is the bright, rounded concentration of light at the center of the disk, the hub from which the spiral arms appear to emerge. The nature of the Milky Way's bulge has been debated extensively. Early models treated it as a classical bulge, a smooth, ancient population of stars formed early in the galaxy's history through rapid collapse or merger events, similar to a small elliptical galaxy embedded at the center of the disk. More recent observations, particularly from infrared surveys that can penetrate the dust, have revealed a more complex picture. The bulge appears to be at least partly a pseudo-bulge, a structure that formed not through early collapse but through the secular evolution of the disk itself. The bar, rotating at the center of the galaxy, can buckle vertically over time, puffing up above and below the plane to create a boxy or peanut-shaped structure that resembles a classical bulge when viewed from certain angles, but is actually a dynamical extension of the bar. This distinction matters because it tells us something about the history of the Milky Way. A classical bulge would imply a violent early history, major mergers, rapid star formation, early assembly from large building blocks. A pseudo-bulge implies a quieter history, gradual internal evolution, disk instabilities, secular processes acting over billions of years. The current evidence suggests the Milky Way's bulge is primarily a pseudo-bulge, though it may also contain a smaller classical component formed during the galaxy's earliest epoch. The stars within the bulge are predominantly old. Many of them formed more than 10 billion years ago, during a period when the galaxy was still young and star formation rates were much higher than today. They are metal-rich compared to the halo stars, reflecting the fact that the inner galaxy had already been enriched by multiple generations of stellar nucleosynthesis by the time these stars formed. Their orbits are complex, influenced by the bar, the disk, and the deep gravitational potential well of the central mass concentration. Moving through the bulge feels different from anything we have experienced on this journey. The stars are closer together. The background glow is continuous, a warm amber radiance created by billions of old stars, blending their light into a smooth, luminous field. Individual stars are harder to pick out against this background, their light merging with the collective glow of the surrounding population. Dust lanes still thread through the region, dark ribbons cutting across the brightness, but even they are being overwhelmed by the sheer density of starlight. The gravitational environment here is intense. The mass enclosed within our distance from the center is enormous, tens of billions of solar masses of stars, gas and dark matter all pulling inward. Orbital speeds are higher. Stars move faster. The galactic rotation curve, which describes how orbital velocity changes with distance from the center, reaches its peak values somewhere in the inner galaxy, before flattening out into the broad plateau that characterizes the outer disk. This flattening of the rotation curve is one of the most important observations in modern astrophysics. In a galaxy whose mass were concentrated only in its visible stars and gas, orbital velocity would decrease with distance from the center, much like the orbital speeds of planets decrease with distance from the Sun. Instead, the rotation curve remains flat or even rises slightly out to the farthest distances measured, implying that the galaxy contains far more mass than can be accounted for by its visible components. This additional mass is dark matter, an invisible substance that neither emits nor absorbs light, detectable only through its gravitational influence on the things we can see. Dark matter forms an enormous halo around the Milky Way, extending far beyond the visible disk, encompassing the entire galaxy in a vast, diffuse sphere of gravitational influence. The total mass of the dark matter halo is estimated to be roughly 10 to 20 times the mass of all the visible matter in the galaxy combined. It is the dominant component of the Milky Way by mass, and yet it remains one of the least understood aspects of the galaxy. Its nature is unknown. Its composition is debated. Decades of experiments have failed to identify the particle or particles that make it up, and yet its gravitational effects are unmistakable in the rotation curve of galaxies, in the bending of light from distant sources, in the large-scale structure of the universe itself. Here, deep inside the galaxy, dark matter is present but less dominant than in the outer regions. The visible matter, stars, gas, dust, is concentrated enough in the inner galaxy to account for most of the local gravitational field. It is only at larger distances beyond the visible disk that dark matter becomes the primary contributor to the galaxy's mass budget. But its influence reaches everywhere, shaping the overall potential well in which all the visible structures exist. We are now well inside the bulge, perhaps 3,000 or 4,000 light-years from the galactic center. The density of stars around us is extraordinary. The dust is thick but not impenetrable at infrared wavelengths. The glow of the inner galaxy fills everything, a warm, continuous light that comes from every direction simultaneously. There is no dark sky here. There are no empty patches. Every line of sight passes through thousands of stars, their light blending together into a luminous fog. And somewhere ahead, hidden within this brilliance, the galactic center waits, the supermassive black hole, the gravitational anchor of the entire Milky Way, the point around which everything we have seen tonight, the outer disk, the halo, the spiral arms, the bar, the bulge, the 400 billion stars, revolves in a slow, patient, eternal orbit. We are close now, closer than we have been at any point on this journey. The remaining distance is measured in thousands of light years, not tens of thousands. The structures ahead are among the most extreme and fascinating in the entire galaxy. The central molecular zone, with its massive clouds of turbulent gas. The nuclear stellar disk, packed with stars at densities found nowhere else in the Milky Way. And at the very heart of it all, the radio source known as Sagittarius A star, the electromagnetic signature of the supermassive black hole that anchors our galaxy. The journey continues inward. The light grows brighter, the stars grow closer, and the center draws us forward with the same patient gravity that has held the Milky Way together for 13 billion years. We are inside the bulge now, deep within the gravitation embrace of the inner Milky Way, and the galaxy around us has become something unrecognizable compared to the quiet outer regions where our journey began. The stars are everywhere, not scattered like the sparse populations of the outer disk, not clustered like the young groups inside the spiral arms, but packed together in a continuous luminous field that stretches in every direction. Individual stars are still distinguishable if you focus on them, but the collective glow of billions of neighbors fills every gap between them, creating a warm amber radiance that has no equivalent anywhere in the outer galaxy. There is no true darkness here. There are no empty patches of sky. Every line of sight passes through so many stars that the background is never black. It is always faintly luminous, always warm, always filled. And yet, paradoxically, much of what lies ahead of us is hidden. Dust, the same interstellar dust that created dark lanes in the spiral arms, that absorbed the light of background stars and re-emitted it as faint infrared radiation, is concentrated here in enormous quantities. Between our current position and the galactic center itself, thick clouds of dust and gas block visible light so effectively that if we were observing from Earth with an optical telescope, we would see nothing at all in this direction. The galactic center is invisible at optical wavelengths. It has been invisible for the entire history of human astronomy. Every ancient civilization that looked up at the Milky Way and wondered what lay at its heart was looking at a wall of dust, not the center itself. It was only in the 20th century, with the development of radio astronomy and later infrared astronomy, that scientists could finally penetrate those curtains and begin to map the structures hidden within. What they found was extraordinary: the central molecular zone. This is a vast, dense, turbulent region of molecular gas, occupying the innermost few hundred parsecs of the galaxy, roughly the innermost 1,000 light-years surrounding the galactic center. It contains an estimated 60 million solar masses of molecular hydrogen, compressed into clouds that are far denser, far warmer, and far more turbulent than any molecular clouds found in the disk. The conditions here are extreme by galactic standards. Gas temperatures are higher, pressures are greater, magnetic fields are stronger, cosmic ray fluxes are intense, and the tidal forces generated by the enormous mass concentration at the center shear and distort the clouds in ways that would be impossible farther out. Star formation does occur within the central molecular zone, but it occurs differently than in the spiral arms. The conditions that govern whether a cloud collapses to forms stars are altered here. The higher temperatures and turbulence provide additional support against gravitational collapse, meaning that clouds must reach higher densities before star formation can begin. The tidal forces from the central mass concentration tear apart clouds that would have collapsed easily in the outer galaxy. As a result, the star formation rate in the central molecular zone, relative to the amount of available gas, is lower than might be expected. There is an enormous reservoir of raw material, but the extreme environment makes it more difficult for that material to convert into new stars. When stars do form here, however, they can form in spectacular fashion. The Arches cluster and the quintuplet cluster, both located within a few hundred light-years of the galactic center, are among the densest and most massive young stellar clusters in the entire Milky Way. The Arches cluster alone contains roughly 1,000 stars, packed into a volume only a few light-years across, including some of the most massive and luminous stars known in the galaxy. These stars burn with extraordinary intensity, their combined luminosity millions of times that of our Sun. Their lifetimes measured in only a few million years. They were born recently by astronomical standards, and they will die soon, exploding as supernovae and scattering their heavy elements into the already enriched gas of the central molecular zone. The quintuplet cluster, discovered through infrared observations that could penetrate the heavy dust, contains similarly extreme stars, including the Pistol Star, one of the most luminous stars ever identified in the Milky Way. The Pistol Star radiates energy at a rate roughly 10 million times that of the Sun. It has already shed enormous quantities of mass through powerful stellar winds, creating a vast nebula around itself that glows with the energy being poured into it. Stars like this cannot exist for long. Their prodigious energy output consumes their fuel at an extraordinary rate, and they are destined to end their lives in violent explosions that will briefly outshine billions of ordinary stars. These clusters and their extreme stellar populations are products of the unique environment near the galactic center. The gas here is dense enough, despite the hostile conditions, to occasionally form massive concentrations that collapse rapidly and produce clusters of extraordinary density and luminosity. They are rare events, even by galactic standards. But when they occur, they create some of the most impressive stellar objects in the entire Milky Way. As we continue inward through the central molecular zone, the complexity of the environment becomes overwhelming. Gas clouds move at high velocities, driven by the gravitational field of the central mass, by the interactions between clouds, by the energy injected by supernovae and stellar winds, and by the influence of magnetic fields that thread through the region in complex, tangled configurations. Radio observations have revealed intricate, filamentary structures, long, thin threads of magnetized gas stretching across tens of light years, aligned along the galactic magnetic field, their origins still not fully understood. These filaments are among the most mysterious structures in the inner galaxy. Some appear to be tracing magnetic field lines, illuminated by the synchrotron radiation of high-energy electrons spiraling along them. Others seem to be the result of interactions between stellar winds and the surrounding medium. Their precise nature remains a topic of active research, but their presence underscores the complexity of the physical environment near the galactic center, a place where gravity, magnetism, radiation, and turbulence all interact in ways that have no parallel in the calmer regions of the outer disk. We are now within a few hundred light years of the center. The stellar density here is astonishing. In the solar neighborhood, the nearest star is more than 4 light years away. Here, stars are separated by light weeks or even light days. A planet orbiting one of these stars would see a night sky blazing with thousands of brilliant points, many of them close enough to cast visible shadows. The Milky Way as a band across the sky would be meaningless. The entire sky would be the Milky Way, a continuous dome of starlight, broken only by the dark silhouettes of intervening dust clouds. The nuclear stellar disk occupies the innermost region, a flattened concentration of stars roughly 500 light-years in diameter, rotating around the galactic center with orbital speeds far higher than anything in the outer galaxy. Stars here complete their orbits in millions of years rather than hundreds of millions. They move fast, driven by the enormous mass enclosed within their orbital radius. The gravitational field intensifies with every light year we cross inward, and the dynamics of the stellar population reflect that intensity. Faster orbits, more complex trajectories, more frequent close encounters between stars. Within the nuclear stellar disk, the stellar population is a mixture of ages. Old stars, formed billions of years ago during earlier episodes of central star formation, coexist with younger stars formed more recently from the gas of the central molecular zone. The chemical enrichment of these stars is among the highest in the galaxy, reflecting the long history of stellar nucleosynthesis in the densely populated central region. Elements heavier than iron, produced in the extreme conditions of supernova explosions and neutron star mergers, are more abundant here than anywhere else in the Milky Way. This chemical richness tells a story of intense recycling. Stars form, burn through their fuel, explode, scatter their processed material back into the interstellar medium, and that enriched material is then incorporated into the next generation of stars. In the outer galaxy, this cycle proceeds slowly, with long intervals between generations. Here, near the center, the cycle has run faster and more frequently, producing a stellar population that carries the accumulated chemical legacy of billions of years of concentrated stellar activity. We are close now, very close. The structures around us are measured in tens of light years, rather than hundreds or thousands. The gas grows denser, the stellar velocities increase, the radiation environment becomes more intense, and ahead of us, detectable in radio waves, in infrared, in X-rays, a compact and extraordinarily powerful source of energy marks the precise gravitational center of the Milky Way. Sagittarius A, the name refers to a complex of radio sources located in the direction of the constellation Sagittarius as seen from Earth. The region is intricate, containing multiple overlapping structures, supernova remnants, ionized gas clouds, hot plasma, and magnetic filaments all compressed into a relatively small volume near the galactic center. But within this complex, one source stands apart. Sagittarius, a star. This is the compact radio source that marks the position of the Milky Way's supermassive black hole. It is not the black hole itself. Black holes emit no light but the electromagnetic radiation produced by material in the immediate vicinity of the black hole, heated and accelerated to extreme energies as it spirals inward. The radiation from Sagittarius A star is relatively faint compared to the active galactic nuclei of some other galaxies, suggesting that the Milky Way's central black hole is currently in a quiet state, accreting material at a relatively low rate. But its gravitational influence is beyond question. We stand at the threshold of the most extreme gravitational environment in the galaxy. Everything we have crossed, the halo, the disk, the spiral arms, the bar, the bulge, the central molecular zone, all of it orbits this point. All of it is held in place by the mass concentrated here, and the nature of that mass, the physics of what happens at the very center of the Milky Way, is one of the most remarkable stories in all of astronomy. The next stage of our journey will take us there, into the immediate neighborhood of Sagittarius A star, past the orbiting stars that have revealed its mass, into the region where space and time bend under the influence of 4 million solar masses, compressed into a volume smaller than our solar system. We are almost at the heart of the galaxy, and the heart is patient. It has been waiting for 13 billion years. The innermost light years of the Milky Way are unlike anything else in the galaxy. We have traveled from the quiet outer disk, through the ancient halo, across the spiral arms with their glowing nebulae and young stellar clusters, through the interarm spaces, past the galactic bar, into the dense bulge, and through the turbulent central molecular zone with its extreme star-forming clusters and magnetized filaments. Every stage of the journey brought increasing density, increasing complexity, increasing gravitational intensity. And now, within a few dozen light years of the precise center, the galaxy reveals its most extraordinary environment. The stellar density here is the highest anywhere in the Milky Way. Stars are packed so closely together that the average distance between them is measured in light weeks or light days rather than light years. A civilization living on a planet in this region would never experience true darkness. Their sky would blaze with tens of thousands of visible stars, many of them bright enough to cast shadows, creating a permanent twilight, even on the side of the planet, facing away from its parent star. The concept of constellations would be meaningless. The concept of a dark night sky would be unknown. And at the exact center of this extraordinary stellar concentration, something sits that emits almost no light of its own. Sagittarius, a star, is the compact radio source that marks the position of the Milky Way's supermassive black hole. It was first detected in 1974 by astronomers Bruce Ballack and Robert Brown, who identified an unusually compact and bright radio source at the galactic center using interferometric observations. At the time, the nature of the source was uncertain. It was clearly unusual, far more compact than any known radio source in the region. But proving it was a supermassive black hole required decades of additional observation and a completely different approach to the problem. That approach came through the patient tracking of individual stars orbiting the galactic center. Beginning in the early 1990s, two independent research teams, one led by Reinhard Genzel at the European Southern Observatory, the other by Andrea Ghez at the Keck Observatory, began monitoring the motions of stars in the immediate vicinity of Sagittarius A star, using infrared observations that could penetrate the heavy dust obscuring the region. Over years, and then decades, they tracked the positions of dozens of stars as they moved through the extreme gravitational field near the center, plotting their orbits with increasing precision. The results were remarkable. The star known as S2 became the most important. S2 orbits Sagittarius, a star on a highly elliptical path, completing one full orbit approximately every 16 years. At its closest approach, S2 passes within roughly 17 light hours of the central object, an extraordinarily small distance by galactic standards, closer than 3 times the distance from our Sun to the orbit of Neptune. At that closest point, S2 moves at nearly 3% the speed of light, roughly 11,000 kilometers per second, driven by the immense gravitational pull of whatever lies at the center. By tracking the complete orbit of S2 and several other nearby stars, both teams were able to calculate the mass of the central object with extraordinary precision. The result was approximately 4 million times the mass of the Sun, compressed into a region smaller than our solar system. No known physical object other than a black hole can concentrate that much mass into so small a volume. The case for a supermassive black hole at the center of the Milky Way, which had been building for decades through indirect evidence, was effectively closed. In 2020, Reinhard Genzel and Andrea Ghez were awarded the Nobel Prize in Physics for this work, sharing the prize with Roger Penrose, whose theoretical contributions to the understanding of black hole formation provided the mathematical foundation upon which observational discoveries like theirs could rest. The black hole itself is defined by its event horizon, the boundary beyond which nothing, not even light, can escape. For a black hole of 4 million solar masses, the event horizon has a radius of roughly 12 million kilometers, comparable to the size of Mercury's orbit around the Sun. This is extraordinarily small by astronomical standards. The entire mass of 4 million suns is contained within a sphere smaller than a modest stellar orbit, creating a gravitational environment so extreme that the predictions of general relativity, Einstein's theory of gravity, become not merely relevant but essential for understanding what happens there. Near the event horizon, space-time is curved so severely that familiar concepts begin to break down. Time runs slower, light bends. The paths that objects follow through space are distorted by the curvature of the gravitational field. At the event horizon itself, the escape velocity equals the speed of light, meaning that crossing this boundary is a one-way journey. Anything that falls beyond the event horizon matter, radiation, information is permanently removed from the observable universe. It contributes its mass and energy to the black hole, but can never communicate with the outside again. And yet, despite this extraordinary gravitational power, the Milky Way's central black hole is remarkably quiet. Compared to the supermassive black holes at the centers of some other galaxies, Sagittarius A star is nearly dormant. Active galactic nuclei found in galaxies where the central black hole is actively consuming large quantities of gas can outshine their entire host galaxy, producing jets of relativistic particles that extend for thousands of light years and radiating across the electromagnetic spectrum with extraordinary luminosity. Sagittarius, a star, does none of this. Its accretion rate, the rate at which it is currently consuming surrounding material, is extremely low. It radiates at a tiny fraction of its theoretical maximum luminosity, emitting primarily in the radio and infrared, with occasional flares in X-rays that last only minutes before fading. The reason for this quietness is simply a lack of available fuel. The immediate vicinity of the black hole contains relatively little gas at the present time. The accretion disk, the swirling structure of material spiraling inward toward the event horizon, is thin and faint, far less substantial than the brilliant disks surrounding actively feeding black holes in distant galaxies. The Milky Way's central black hole is essentially resting, having consumed or expelled most of the material in its immediate environment during earlier, more active phases of the galaxy's history. But it has not always been this quiet. Evidence suggests that Sagittarius A star experienced periods of much higher activity in the past. Observations of structures called the Fermi bubbles too, enormous lobes of high-energy gas, extending above and below the galactic plane for roughly 25,000 light-years, suggest that a powerful outburst from the galactic center occurred several million years ago, injecting vast amounts of energy into the surrounding medium. The exact cause of this outburst remains debated, but the feeding of the central black hole during a period of higher accretion is one of the leading explanations. In 2019, the Event Horizon Telescope collaboration released the first direct image of a supermassive black hole, captured not of Sagittarius A star, but of the much larger black hole at the center of the galaxy M87. 3 years later, in 2022, the collaboration released an image of Sagittarius, a star itself a blurred but unmistakable ring of light surrounding a dark central shadow produced by radio emission from hot gas orbiting just outside the event horizon. The image was technically far more challenging to produce than the M87 image, because the Milky Way's black hole is much smaller and the gas around it changes configuration on timescales of minutes rather than days, making the signal difficult to stabilize. But the result confirmed what decades of stellar orbit tracking had already established: a compact, massive object consistent with a supermassive black hole sits at the precise center of our galaxy. We are here now in the presence of that object. Not at the event horizon. Nothing that reaches the event horizon returns, but in the surrounding region, the inner parsec, where the S-stars trace their rapid orbits, and the faint glow of the accretion flow marks the location of the black hole against the blazing background of the nuclear star cluster. From this vantage point, the black hole itself is invisible. It emits no light. It casts no shadow visible to the eye. Its presence is known only through its effects, the curved paths of nearby stars, the faint radio glow of heated gas, the gravitational lensing of background light, and the sheer dynamical evidence of 4 million solar masses concentrated into a volume smaller than a single stellar system. It is quiet here, not the quiet of the outer galaxy, where emptiness creates silence. This is a different kind of quiet. It is the quiet of tremendous power at rest. The black hole is not pulling the galaxy apart. It is not consuming nearby stars. It is not radiating destructively. It is simply sitting at the center of the Milky Way's gravitational potential, anchoring the orbits of hundreds of billions of stars, holding the galaxy together not through violence, but through the patient, constant, unremarkable application of gravity across 13 billion years. The stars around it orbit swiftly. The gas near it glows faintly. The universe beyond the event horizon is permanently hidden. But the black hole asks nothing of the galaxy except to orbit, and the galaxy complies. This is the heart of the Milky Way. 4 million solar masses silence at the center of everything we have crossed tonight, and it has been here in one form or another since the galaxy was young. Supermassive black holes are believed to form early in the lives of galaxies, growing through the accretion of gas and the merger of smaller black holes during the chaotic assembly period, when galaxies themselves were taking shape. The Milky Way's central black hole has likely been present since the first billion years of the galaxy's existence, growing slowly over cosmic time, anchoring the successive generations of stars and structures that accumulated around it. It has witnessed every phase of the Milky Way's evolution. The formation of the halo, the assembly of the disk, the ignition of the spiral arms, the birth and death of hundreds of billions of stars, the absorption of smaller galaxies, the slow enrichment of the interstellar medium with heavier elements, the eventual formation of our sun, our planet, and everything that followed. All of it has orbited this center, held in place by this mass, organized by this gravity. We have reached the destination of our journey, the galactic center, the anchor point, the gravitational heart around which the entire Milky Way revolves. And from here, with the dense nuclear star cluster blazing around us, and the silent black hole resting at its core, there is only one thing left to do: turn around and look outward, across the full breadth of the galaxy we have just crossed. From the center of the Milky Way, the view outward is unlike anything we have experienced on this journey. We have spent the entire night moving inward, from the sparse outer disk, through the ancient halo, across the spiral arms, through the interarm spaces, past the galactic bar, into the dense bulge, through the turbulent central molecular zone, and finally to the supermassive black hole at the gravitational heart of everything. Every stage brought us deeper. Every chapter brought us closer. And now, standing at the center, surrounded by the blazing nuclear star cluster and the silent presence of Sagittarius, a star, we turn and face outward for the first time. The galaxy stretches away from us in every direction. From this vantage point, the disk extends outward like a vast, luminous plane, thinning gradually with distance, its spiral arms winding away toward the outer edges where starlight fades and the halo begins. The bulge surrounds us, its billions of old stars forming a warm, glowing shell that thickens above and below the midplane before tapering into the broader disk. Through gaps in the dust, and there are gaps, even here, the distant structures of the galaxy are visible in infrared and radio wavelengths stretching across tens of thousands of light years, each one a region we have already crossed, each one carrying its own character, its own populations, its own contribution to the story of the Milky Way. It is a perspective that no human being has ever experienced. No spacecraft has ever traveled far enough from the suns to see the galaxy from outside, let alone from its center. Everything we know about the Milky Way's large-scale structure has been assembled from within, pieced together from observations made from a single point, roughly 26,000 light-years from the center, using instruments that can see only a fraction of the galaxy at any given time. The full picture, the spiral arms, the bar, the bulge, the halo, the globular clusters, the satellite galaxies, the dark matter halo, is a composite, a reconstruction built from billions of individual measurements, each one revealing a small piece of the whole. And yet the reconstruction is remarkable. Over the past century, astronomers have mapped the Milky Way with increasing precision, using radio surveys to trace the distribution of hydrogen gas, infrared surveys to count and classify stars hidden behind dust, proper motion measurements to determine how stars move through space, spectroscopic observations to determine their chemical compositions, and parallax measurements to determine their distances. Each technique reveals a different aspect of the galaxy, and together they form a picture that is detailed, self-consistent, and continuously improving. The Milky Way that emerges from these observations is a galaxy of extraordinary complexity. It is not a simple disk of stars rotating around a central point. It is a multi-component system: thin disk, thick disk, bar, bulge, halo, globular cluster system, satellite galaxy system, gas disk, dust distribution, magnetic field, cosmic ray population, dark matter halo, each component with its own history, its own dynamics, its own contribution to the whole. Understanding any one component requires understanding how it interacts with all the others. The galaxy is not a collection of parts. It is a system, and the behavior of the system emerges from the interactions between its components across billions of years. This is what we have traveled through tonight. Not a static landscape, but a living system. A galaxy that formed from the gravitational collapse of primordial gas more than 13 billion years ago, that assembled itself through the merger and absorption of smaller structures, that built its disk through the gradual settling of gas into a rotating plane, that generated its spiral arms through density waves, propagating through that disk, that forged its heavy elements through successive generations of stellar nucleosynthesis, that grew its central black hole through accretion and merger, and that continues to evolve today, slowly, patiently, on timescales that dwarf human comprehension. The Milky Way is not finished. It is still changing. New stars are still forming in the spiral arms. Old stars are still dying and returning their processed material to the interstellar medium. The bar is still rotating, channeling gas inward, influencing the orbits of billions of stars. Satellite galaxies are still being absorbed, their stars stripped away and incorporated into the halo. And the galaxy itself is still moving through intergalactic space, part of a larger structure called the local group, gravitationally bound to the Andromeda galaxy, which is approaching at roughly 110 kilometers per second. In approximately 4 to 5 billion years, the Milky Way and Andromeda will collide. This event, sometimes called the Milkomeda merger, will fundamentally transform both galaxies. Their disks will be disrupted, their spiral arms will be destroyed, their stellar populations will be mixed and redistributed. Their central black holes will eventually merge, producing a single, more massive black hole at the center of a new, larger galaxy. The result will likely be an elliptical galaxy, a smooth, rounded collection of stars, without the organized disk and spiral structure that currently define both the Milky Way and Andromeda. This merger will not be violent in the way collisions seem on human scales. The distances between individual stars are so vast that direct stellar collisions will be extraordinarily rare. Most stars will simply have their orbits altered by the changing gravitational field, drifting into new trajectories within the merged system. Our own sun, if it still exists at that time, will likely survive the merger intact, though its position within the new galaxy will bear no resemblance to its current orbit within the Milky Way's disk, but that is billions of years from now. Tonight, the Milky Way is still a barred spiral galaxy, still rotating, still forming stars, still evolving through the slow processes that have shaped it since its formation. And from the center, looking outward, the full scope of that evolution is visible in the distribution of light, gas, dust, and dark matter that extends in every direction. The journey we have taken tonight covered roughly 100,000 light years, from the outer halo to the galactic center and back in perspective. We passed through regions of extraordinary variety, the sparse outer disk, where ancient metal-poor stars drift in near isolation, the halo, where globular clusters orbit on trajectories set 12 billion years ago, the spiral arms, where new stars ignite inside collapsing molecular clouds, the interarm spaces, where the galaxy rests between creative pulses, the galactic bar, where gravitational resonances channel gas and shape orbits, the dense bulge, where billions of old stars create a continuous warm glow, the central molecular zone, where extreme conditions produce the most massive young clusters in the galaxy, and the nuclear region, where a supermassive black hole 4 million times the mass of our sun sits in patient gravitational silence. Each of these regions is part of the same galaxy. Each is connected to the others by gravity, by the flow of gas, by the exchange of energy and matter, by the continuous cycling of elements from stars to interstellar medium and back again. The Milky Way is not a collection of separate environments. It is one system, one structure, one slowly evolving entity that contains within itself the full range of astronomical phenomena, from the coldest molecular clouds to the hottest stellar surfaces, from the densest neutron stars to the most diffuse regions of the halo, from the youngest protostars to the oldest surviving stellar populations in the universe. And somewhere within it, on a small rocky planet orbiting an unremarkable yellow dwarf star in a minor spiral arm, roughly halfway between the center and the edge, a species has spent the last few centuries learning to see beyond its own sky and understand the galaxy it belongs to. That understanding is still incomplete. There are structures within the Milky Way that remain poorly mapped. The far side of the galaxy, obscured by the dust and crowding of the inner disk, is still largely uncharted. The exact number of spiral arms, their precise positions, and their connections to the bar are still debated. The nature of dark matter, which outweighs all visible matter in the galaxy by a factor of 10 or more, remains one of the deepest unsolved problems in physics. The formation history of the bulge, the origin of the thick disk, the detailed merger history preserved in the halo's stellar streams. All of these are active areas of research, each one gradually yielding to the patient accumulation of observational data and theoretical understanding. But what has been learned is already extraordinary. A century ago, the nature of the Milky Way was barely understood. The existence of other galaxies was not yet established. The size of the universe was unknown. The concept of a supermassive black hole at the center of a galaxy would have seemed like science fiction. Today, we can track individual stars orbiting that black hole. We can measure the chemical composition of stars on the far side of the galaxy. We can detect the faint gravitational influence of dark matter in the rotation of the disk. We can observe molecular clouds in the act of collapsing to form new stars. We can reconstruct the merger history of the galaxy from the orbital patterns of halo stars. The Milky Way has become knowable, not fully known, perhaps never fully known, but knowable in the sense that its structures, its processes, its history, and its future can be studied, measured, modeled, and understood with increasing precision and depth. This is what a galaxy is, not simply a collection of stars, but a living system born from the primordial gas of the early universe, shaped by gravity, enriched by the lives and deaths of hundreds of billions of stars, structured by waves and resonances and mergers and slow evolution, and still changing, still growing, still becoming something it has not yet been. We have crossed it tonight, from edge to center, from the ancient halo to the supermassive black hole, through every major structure, every environment, every population. And now, as the journey comes to its end, the galaxy continues, the stars orbit, the gas drifts, the arms glow, with the light of new stars being born. The black hole waits. The dark matter holds everything together. The Milky Way does not need us to observe it. It does not need us to understand it. It existed for billions of years before any eye turned upward to wonder at the faint band of light crossing the night sky. And it will continue for billions of years after every current star has burned through its fuel and faded. But for now, tonight, we have traveled through it. We have seen what it contains. We have understood, at least in part, how it works. And that is enough. The stars drift on, the galaxy turns, and the silence of deep space, the same silence that has filled the Milky Way since its formation, settles gently around us as the journey ends. 100,000 light years of starlight, 400 billion suns, one galaxy, one slow, quiet, ancient home. Rest now. The galaxy will still be here in the morning.